You're welcome to another free structural design class with me. And in this class, we'll be discussing structural engineering, basically, and with load estimation. I'd like you to pay attention in the meanwhile we'll be here together. And this class is supposed to span for 3 days. Today is the day one. Stay with us, and we're going to have a nice time together. I'm Joshua, the designer. Let's get going together.
Tonight I'll just be showing us basic stuff. I promise to show you one of the software I use to run my analysis in about 2 minutes. Then you have your result. And also I will be showing you how to estimate loadings for those of us that might not really be too good with estimation. And at least I'll show you one or two, right? And from there we can build up our adventure into structural designs in the next few days. All right. So um, thank you once again for coming around. All right. For those people making contact with me for the first time, I'm Joshua, and I own a YouTube channel. So I'm also a YouTuber. Right. So you find Joshua the designer there, right? So and we'll be having nice time together in the next 3 days. So to start with, I'm going to share one of the materials I've been working on. I'm actually working on a structural designer's handbook, of which I hope in the next few weeks or months I would release it for you all when it's ready, or when it's fully ready. So that should be for the designers, and that's one of the efforts we're putting together to be sure that things are getting better in the world of engineering. Right. So I'll be sharing my screen right now, just few pages of my design handbook, right? So because it's still in progress, I'll be showing you a few pages, right? So I believe you can see my screen. Can I get a feedback, please? Can I get a feedback?
Yes, we can see your screen.
Okay, great. Now, I would I would like that we start from loadings, and before I just start from there, structural engineering is a very vast field, and I do not want you to see it as a cause and effect thing. How that popularly now people feel once you can actually undo one or two softwares and you can design a building, then you're fit to be a structural engineer or a structural designer. That would not be true, because structural engineering is very broad field, and I would say practically that it gives answers to almost everything that makes life worth living. That is true, right? And that brings me to explaining each time my private students, if some of them are here, would have heard me say each time that a building would behave as a human being. A building would always give reaction as you also give reaction to things, you know, because a building, even though you don't want to believe that a building is living, but I, as a structural designer, have come to discover that a building is alive because it can give reciprocal actions or reactions to whatever it is you post on it, and it will be true. That is to say that if I load a structure, it's going to behave in line with the loading conditions and the kind of load with which it is subjected. If I unload it, it's going to behave to be in that effect. And it means a building as a response, something we call response to stimuli in biology, something like that. It responds. It speaks to you. It tells you I am overburdened. It tells you I can't do more than this. It tells you I'm not feeling fine. It tells you something is not right somewhere. But many designers do not understand these languages, but they go on up front and mess the whole stuff. It means the knowledge of structural engineering as a foundation other than software. It's an ability to understand the interactions that goes or that takes place within your structural framework and the resultant effect and the probable solution to ensure that your building is in safe condition and it is worth the purpose for which it is being constructed in the first instance. Right. So tonight, to shorten our time here together, because this is supposed to be a fundamental session. Right. So, um, many of us would have questions, particularly the beginners in structural designs or structural engineering, and says, how do we design a structure? How do we come about the loadings and all of that? Every structure, be it the ones that people live in or the one that people do not live in, they tend to be subjected to certain loadings. So what I mean by the ones people do not live in, for example, if you have structures like retaining walls, you have um, different kind of structures that way, water retaining structures and all of that, you discover that they are also affected by loadings. So you begin to speak about the pressure in that instance. You speak about the active pressure, the passive pressure. You speak about the overturning moment and all of that. Those are resultant effect of the conditions with which your structure is subjected to, right? So it means that for you to be a human being, there are certain things you need to build resistance against so that your life will worth living. So you want to ensure that your health is in this proper state. You want to ensure that your diet is informed so that you would not collapse a day, your cells would not weaken out and all of that. So the same thing would apply to our structures. And these loadings are so important that you cannot ignore. And that is why each time you discover that many buildings that were built as a residential um, habitation and later on in the future we want to attempt to convert them to a church or to a religious center, you discover that if the designer initially did not cater for that, right, it might actually create a very dangerous scenario. And it would not just happen just by one person's life, it takes several lives. So the concept of loadings and appropriately loading your structure is as important as anything. So you want to know what exactly the loading is. Now I had prepared in this manual. There are so many things in this manual, and I am looking forward to the day where I will be able to confidently share with all structural, all civil or structural designers, upcoming civil or structural designers anyway, right? But for the meantime, it's still under um, how do I say, it's still under arrangement, right? So once it's out, would let you know, right? So if you look at this arrangement, this is a sequence of load transfer between elements of a structure. There is something we call load chase down. I believe in the third day I should show you what load chase down means. So in your softwares, in different softwares, you see something like load chase down analysis. It's a means by which your load is being transferred from one point to another within the same structure. It means that that's why I said your structure is a living thing. For as a structural designer, I'll say it's a living thing because what constitutes a living thing is not only breath. If it were holy breath, then other factors would not be accountable for. But this guy structure can actually transfer from one end to another safely to a bearing strata. It can actually cater for itself such a way that all the loadings have been transferred carefully to ensure a stable formation. Right. So you see my number one, which is okay. So before I get to this place, I had already analyzed different kind of load that we may have. I spoke about several kind of load before now, right? Before these loadings, however, right? But you can just see one, two, three. I have uniformly distributed line loads. So these uniformly distributed line loads, they are um, loads that are shared uniformly over a surface area, actually, or not actually over a surface area alone, but over a considerable span, right? So, and that's why you see that it's always sometimes per meter, per meter, per meter rod. You understand? So, we have a uniform distributed line load, which an example of which is this one, the one we have right here on top of these beams. So this load, uniform distributed load, will be shared evenly across that span. Right. We also have triangular and trapezoidal load. And in this case of triangular and trapezoidal load, we have them when we have slab paneling. Mostly we have it in roof also. We have it a different, it's just a means of sharing loads within a panel, right? So the load might constitute a triangular form or trapezoidal form. And in turn, this will give you how you're supposed to share your load within panels, right? And we also have concentrated point loads. And these concentrated point loads, for example, if you check my load number three, load number three is actually a load from one and two. The load from the slab is being transferred to the beams, and the beam loads is being transferred to the column. And because this column is actually acting as a point element, right? So it's going to exert an axial load, right, down in that point. So it's going to be form like a point load down that place. So even though that's not only the kind of point load we have, a beam can also form a point load. As we go ahead, probably tomorrow, I'll show you how a beam, because tomorrow we are going to touch a little of general arrangement drawing. I have a separate class for general arrangement drawing because it's not something we can just discuss in 30 minutes and we're done, right? But I'll show you how that a beam can constitute a point load on another beam, right? And it will actually need to be treated as a point load if you want to be correct with your analysis. Now, if you check this framework now, you discover that the load transfer is from the roof slab. So we assume that we have roof slab. So you see that my one from this key that I have on my right hand, from this key that is here, I have load from roof slab to beam. That's number one. I also have load shared from roof beam to columns. That's for these two, to the right and to the left. So it depends on what span it is and what eccentricity it carries. And that will determine how much of load will be shared to each columns, right? So this load number three is that which I explained formally about the columns. So all the load that is coming from the roof floor is being transmitted through the columns to the next column and not the beam. So you see that three gets to three. Three never connects to two, and it didn't connect to one. So three gets to another three. So column transfer the loads down that way until it gets to the foundation. So you see that number four is the load transmitted from columns to the foundation. But in this case, we are considering a pad foundation. In the case of raft foundation, the load transfer would not go to a pad footing like this. It spreads around the area. And the principle of a raft foundation is actually the principle of surface area. We have pressure is equals to force over area. So by the time you apply all your, I do not know how much you understand this explanation. By the time you calculate all your loadings right from the roof to the foundation, yeah, you obtain a load, and that's going to be the force, and you have the area of your foundation floor, right? So that combination, that ratio is going to give you a pressure, and that pressure is what you would use to compare the soil bearing pressure that is obtained during the geotechnical analysis, right? So, and you need to understand that the pressure that is obtained from the ratio of your force over area should not exceed that one that has been obtained from your geotechnical report for it to be true. So if it exceeds, there's another means, but that's practically enough for this class. Um, so we can move forward. So I'd explain the kind of loadings and the load transfer, and I would like to just move and skip. Okay, so we have design loads as a civil engineer. Only a very fresh undergraduate would not understand the ultimate design load. For many of us that had gone through the university system or the polytechnic system, or those that are already in part 3, 4, 5, should understand the design load is actually also called the ultimate design load, right? Which factors your dead load and life load. And we should know that the dead load is constituted by the weight of the structure itself and all unmovable or permanent loads within your structure, and which the life load or the imposed load is constituted by temporary loads, moving loads, including you that moves from one point in the building to another, right? So, and that's simple enough to understand. So if you want all these loads, they have their factors, right? So and these factors are not guesswork. We have codes that can actually bring these factors to us as recommended, right? If you check your BS 6399 part 1 1984, in that material I already have that fixed already. So you would find it there in BS 6399 part 1. You find very different load factors for your live load, and you can apply it appropriately. And you see how I do mine when we start to design properly. So I'll show you one of the last things tonight, so that we would meet tomorrow and we'll start the real work, right? So load estimation and distribution. So what I explained in the load transfer or the load chase that one before, now I want to show you how do we now do it using calculations, right? So if I want to estimate load or and I want to distribute load between elements, how do I do it? Now, if you check this is a structural layout, or what some people will call a general arrangement drawing. And it's general arrangement drawing for some of us that do not know what I'm talking about. A general arrangement drawing. I hope what's in the chat. Oh, somebody says he can't hear me. Is that for everyone? Let me be sure. If you can hear me,
I can hear you from my own end here.
okay, great. Obeji Jochin, I believe you can hear me. Okay, so this is a structural layout, otherwise known as a general arrangement drawing. And a general arrangement drawing is a drawing that actually um, shows positions, sizes, and all the details of your structural components within your structures, the positions, the sizes, the spans, and all of that. All the information you need about your structural framework, you find it in a general arrangement drawing. So as you can see here, we have the sizes of the beams, we have the sizes of the slabs, you have the beam dimensions, you have the grid lines, you have the column positions, and you see. Now, I spoke of the fact that your beam can constitute a point load on another beam in the last time. I never knew that I had one in my material. So if you check beam B, I believe everyone can see beam on grid line B. This is what I mean. Beam, this beam you see my cursor on, right? That beam has no column support. If you don't know what I mean by column support, columns are those ones that I have shaded here at the four corners, right? So that those are shaded columns, and they are shaded because they continue. So whenever a column is not shaded, it means it terminates on that floor, right? Depending on the legend or key used by the structural designer, it might vary, but that's the usual standard we find around, right? So the beam on grid line B is directly not supported by columns, but it's supported by beams on grid line 1 and grid line 2. So while you are analyzing beam 1 and 2, the load exerted by beam B would be a point load, a concentrated point load, right? If you understand what I just said, can I have your comment in the chat, please? I want to be sure I'm carrying you along. If you understand what I say, can I have your comment, please? Right. Okay, great. Thank you, Mr. Sheffield. God bless you. So now, many of you would have observed a thing that I believe somebody would have observed, but if no one observed, then I'm afraid. Okay, I said something here. Considering the figure below, which in the right sense, I'm not supposed to be using figures, but I'm using this because I want it to be an interactive designer handbook and not a textbook, which is taken as, I said, considering the figure below, which is taken as two one-way slabs are supported by internal and external beams. Now, I used taken as in capital, right? And you can see in quotes, meaning that that's my assumption. It doesn't mean that that is how it should be. Okay, so you can understand. Let's check. I named one panel 1 and the other panel 2. If you check panel 2, we have something called aspect ratio. I do not know if any of us had come about aspect ratio. Let me see if I can write something on my board. Aspect ratio. Don't mind my writing, please. I'm using the mouse to write. Aspect ratio. Now, this aspect ratio is the ratio of my longer span to my shorter span, right? So we know that if the ratio results to a value less than 2, automatically we can take that to be a two-way slab, a two-way slab. Now, please, the meeting is going to end in 10 minutes according to the Zoom program. So once it takes us offline, you can use the same link to join again, then we'll round off from there, right? But when the aspect ratio is greater than 2, then we can maintain our one way. So this is how we determine one way and two-way slab, right? Now, if you now check my panel 1 says the LY, which is the longer span, and the LX, which is the shorter span. It says that we have LY to be 7 meters and LX to be 2 meters. Now, my ratio would say, can you please, thank you. So my ratio says I have above 2. That should be about 3 points something. So, wow. Hello, can you help me with your microphone, please? Thank you. So the aspect ratio for panel one is greater than 2, and that's why it's valid as one-way slab. But when it comes to panel 2, we have LX to be 4 meters. So the ratio of LY to LX is less than 2. Agreed. So that's supposed to be a two-way slab. Now, but I'll tell you a thing. In school, and I believe that everyone in our classroom would attest to what I want to say rather, that when you obtain a value less than 2, you are supposed to design that place as a two-way slab. That's an academic way of designing, right? But in a professional setting and as a designer who understand principles and how to go about these designs, you can design these as a one way and it will still stand. It will never fail. And that is one of the reasons why we need to have more exposures beyond our classroom and see how things could be done apart from the conventional and old way, right? But I didn't say this the right way, but anyways, if you follow your academic way of doing things, you get the right thing. Follow this way, you get the right thing. But never argue with a man who would do his own this way if he can actually prove that it will stand. Because engineering doesn't have a master rule. It doesn't have one way where all of us could follow to get results, right? So all of us can take different routes, then we still get a workable solution. That's what I'm saying, right? So looking at this now, we agree that I want to take these two panels as one way. I've explained why already. How do I estimate the loads on this slab? So that takes me to load. Hello. Okay, please help us with your microphone each time that you wanted to say or do. So how do I estimate load on my slab? So for my one-way slab, the load distribution is just like this. We want to assume that the floor is for residential purpose, and that we have partition as 1.5 kilonewton per meter square, and our finishes also to be 1.2 kilonewton per meter square. Right? You know, I told you that the live load, we don't just bring a live load factor. So we want to go back to a code, British Standard Code, 639 now, Part 1, 1984, and want to obtain a value for a live load. So we want to go back there and see, since it's a residential, so you see that we have self-contained dwellings units, that's 1.5, which is also residential. If you check for this all, I'm not designing boiler room. I'm not designing communal. No, I'm not designing that. So I want to design bedrooms and dormitories or whatever it is. So I have 1.5 for distributed load. You see that I have a column for distributed load and I have another column for concentrated load. So, but we are using distributed load because we are designing per meter run, right? So we have agreed on 1.5 kilonewton per meter square. I used to have my codes of practice on my drive and I share after tutorial sections like this. But what I'll do is probably after the old training period, all that I've said I would share with you. If someone can actually remind me, I would store them up in my Google Drive and I share the link for everyone to have. Right. So I really want to touch one thing tonight before the time would run out. Right. So we have slab loadings, and this is how we estimate the slab loadings for solid slabs anyway. So for the slab own weight, because I told you that the dead load is made up of um own weight, own weight. So the thickness of that slab is 150 mm, right? So converting that to meters, we have 0.15, and we have the density of concrete, 24, right? So that's, we know that. So we have it in kilonewton per meter square, 3.6. And because we have obtained our finishes and partitions, and we have the values formally, 1.2, 1.5, and these three constitutes our dead load at this level. There are many things that could actually constitute your dead load, right? But at this level, we want to remain at this level. So we have 6.3 as the total value for our dead load. And for our live load, we have 1.5. We were there together and we saw that. Now, for the ultimate design load, I spoke about that already. I said this gives allowance to factor to how to use a partial factor of safety for our dead and life loads, and it gives us the ultimate design load, right? 1.4 GK plus 1.6 QK, and that gives us 11.22 kilonewton per meter square per meter run. Now, this my unit might give you a little issue, but if you know your way around it, it should not. It should not even. There's nothing special. Oh, sorry, there's nothing special about it. But let me just tell you, our slab is always designed per meter run. So our units at this level should be kilonewton per meter, right? So instead of me putting it that way, I can also put it the other way around as 11.22 kilonewton per meter square per meter run. All right. So you understand that when we get to this. Now, the load that we obtain for our slabs can safely be transferred to our beams. And I'll see if we can run that one in 1 minute so that would probably shift the next discussion to the tomorrow. Yes, and I think we would need to do that. Please pardon me for tonight. Tomorrow will be a full day together. We have extended time, right? So we have estimated the slab load. So to convert, we want to actually transfer load from this panel one. And this panel one is a simply so what did I say? Is a one-way slab rather, right? So we want to transfer load from this panel, just the way I've shown it with these colors in this panel one, to beam A and beam B, right? So if you check beam from panel one, beam A1 to 2, which is this beam A, grid line 1 to grid line 2, and beam B, grid line 1 to grid line 2. If we want to transfer that load, because it's a one-way slab, it is assumed to be shared equally on both sides. So the formula that you use is NLX over 2, where the N is the ultimate design load, right, that we obtained formally, the one that has 1.4 GK plus 1.6 QK, right? So having applied NLX, that LX is your short span. And we have already agreed that this side is the short span and this is the long span. Right, we have less than 1 minute. Once this meeting cuts, use the link again. Let's get going, guys. So with that, we can have this value 11.22 kilonewton per, right? So that goes to beam A and beam 2. Now, if you intend to convert this, wow, this person is still disturbing us. Let me look for the person. Okay. So if you intend to convert this to a point load, you can multiply by that span, which is 7 meters, right? So that gives us 78.54, right? I really hope that you get what I'm saying. I really do hope. The same thing applies to panel 2 by using NLX over 2, where N is our ultimate design load 11.22 obtained before. You'd have a value that is being shared between this particular beam and this beam. So to say that beam A and beam B shares equal load from panel 1, which is this panel on my left. Beam B and beam C shares equal load from panel 2 because we are considering them as one-way slabs, these two panels. Nonetheless, you'd consider that beam B carries two addition, two loads from two panels. So um, obviously, it is more loaded than every other beams in this framework, right? And I would have loved us to now